All right, now let's look at the next example. Let S equals 2, 3, 4, 5, 6, 7, 8, 9, 10 with relation R defined as follows. So we want to consider the dividing relation that we discussed before. So A, R, B, if A divides B, okay, so this is the relation we want to define. So find the maximal, minimal, maximum, minimum of this set S together with the dividing relation. Of course, if they exist. Okay, so let's look at the hash diagram for this example. So in a hash diagram, remember how do we create the hash diagram? We said if you have two elements, let's say A and B. Now if A are B, or another notation was A curly less than or equal B, curly less than or equal to, same as the relation. So you can either say A are B or A curly less than or equal to B, means if A is in relation with B, then in hash diagram, we would consider B above A. So we would write it this way. If we write A, B above A, then that means A is in relation with B. Now, in our case, what is in relation with what? So again, remember, if A is in relation with B, we have to put B above A. Now here, the first element of S is 2. So we have 2 here, and 2 is in relation with 4, right? Because 2 divides 4. Remember, our relation here is dividing. So A is in relation with B if A divides B. So 2 divides 4, so 2 is in relation with 4. And 2 divides 6, so 2 is in relation with 6. 2 divides 8, so 2 is in relation with 8. But also another thing is 4 also divides 8, right? So I have to put 8 on top of 4. So the one that I first wrote was not correct, because 8, yes, 8 has to be above 2, but it has to be also above 4 as well, right? Because 2 divides 8, but 4 also divides 8, right? So 2 divides 4 and 4 divides 8. So 2 divides 4 means 4 is on top of 2. 4 divides 8 means 8 is on top of 4. But for example, 6 does not divide 8. So 8 will not be on top of 6. So I should not connect them with an edge like this, right? Because 6 is not dividing 8. What else can we say? So 2 also divide 10, but none of these numbers divide 10. 4 does not divide 10, 6 does not divide 10, right? 8 does not divide 10. So 10 will be on top of 2, but not on top of any of these elements. So let's say I can put 10 here. Okay. And then also 5 divides 10. So 10 has to be on top of 2, also on top of 5. And what else do we have in this set S? Remember, S is elements 2 to 10. So there we also have 3. Well, 3 divides 6. So I can put 3 here. Maybe to make it a little bit neat. I can put 10 this side and 5 here, and then 3 here, which divides 6. Also 3 divides 9. But again, 6 does not divide 9, right? So 3 divides 6, 3 divides 9. So 6 on top of 3 and on top of 2, 9 only on top of 3, 4 on top of 2, 10 on top of 2 and 5, and 8 on top of 4. So 2, 3, 4, 5, 6. Okay, we also need 7. Where is 7? 7 is a prime number. It's just one number by its own, 7 does not divide any of these numbers in S. But if S was continuing until 14, then I should write 14 on top of 7, but S only contains 2 to 10. So 7 is just an isolated point. And I think we listed all of them, right? So 7 is not on top of anything either. So nothing on top of 7, because 7 does not divide any of these numbers, and 7 is not top of anything as well, because none of these numbers divide 7. If S started from 1, then I should write 1 below 7, because 1 divides 7, but S does not contain 1. So 7 is an isolated point here. And we have the rest of element. I think I listed all elements, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Now let's look at the maximal, minimal, maximal, minimal, and maximum, minimum. So maximal means an element is maximal if nothing is above it. So maximal A is maximal if no element lies above it. So let's see. So that means 8 is maximal because no element is above 8. 4 is not maximal because we have 8 above 4. 2 is not maximal because we have 4 above 2. 10 is maximal, nothing above 10. Nothing above 6 either. So 6 also maximal. 9 also maximal. 7 also maximal. Yeah, 7 is an isolated point, but nothing lies above 7, right? So 7 is also maximal. 3 is not maximal because we have 9 above 3 and also 6 above 3. Yeah, so these are the maximal. Most elements are maximal, but 4 and 5 and 2 and 3 are not maximal because we have elements lying above them. That's it. So this is for maximal. Now for minimal. You can say A is minimal if no element lies below it. So no element lies below 5, for example. Below 10, we have 5, so 10 is not minimal. Below 8, we have 4, not minimal. Below 4, we have 2, not minimal. But we have nothing below 2, so this is also minimal. We also have nothing below 3, so this is also minimal. But below 9, we have 3, so that's not minimal. What about 7? Well, 7, we saw it's maximal, but it's also minimal. And minimal. Because it's an isolated point, as we said, so nothing lies above it and nothing lies below it either. So at the same time, it's maximal and minimal. Okay, what about maximum, minimum? So maximum A is maximum if A lies above all other elements. And here we don't have such number. We don't have a number that lies above all other numbers. So for example, look at here, 10, well, yes, 10 lies above 5 and 2, but 10 does not lie above 4 or does not lie above 8, for example. 8 lies above these elements, but 8 is not above 6, for example. 6 is not above 9, for example. 9 is not above 7, for example. 7 is not above anything. So none of the elements here are maximum. So in figure above, no element lies above everything else. Everything else. So that means we have no maximum. So for minimum, A is minimum if A lies below all other elements. Again, here we don't have a element that lies below everything else. For example, 5 lies below 10, but does not lie below 4, for example. 2 lies below 10, 4, 6, and 8, but 2 is not below 9, for example. 3 is not below 4, for example. 9 is not below 6. 8 is not below anything. 7 is not below anything. So we don't have an element that lies below everything else, right? So again, I can say that in figure above, there is no element that lies below all other elements. And that means we have no minimum either. We have no minimum. Okay, so now I want to give you, so this is an example where we had maximal and minimal. So in fact, more than one maximal and minimal, more than one maximal, more than one minimal, but no maximum and no minimum, no maximum and no minimum. The next definition I want to talk about is least upper bound and greatest lower bound of a set. So let S with this curly less than equal, which is like a relation R, be a poset. And let's say A be a subset of S. Okay, we say that B in S is an upper bound for A if for every A in A, we can say that A is curly less than equal to, because my relation is curly less than equal, which could be actual less than equal, or could be dividing, could be subset, any poset. if for every a less than, if for every a in A, we have A clearly less than or equal to B. Similarly, B, or let me say C in S is a lower bound for A if for every A in A, you can say that C is clearly less than or equal to A. Okay, so these are the definitions of upper bounds and lower bounds of a set. Now, another concept is the concept of least upper bound and greatest lower bound. So again, let S together with, clearly less than equal be a poset, and let A be a subset of S. We say that let's say U in S is the least upper bound for A if if for every A in A, so let's say this way, if U is an upper bound, U is an upper bound for A, and U is less than or equal to B for every upper bound B for A. So you can guess from the name, the least upper bound. The least upper bound for a set A, first of all, it has to be an upper bound. Like I said, from the name, you can guess that the least upper bound, first of all, has to be an upper bound. So when do we say that U is the least upper bound? If first of all, U is an upper bound, and it has to be the least upper bound, meaning that if you consider any other upper bound for A, like B, U has to be less than or equal to that. Right? So least upper bound means an upper bound which is less than or equal to any other bound, any other upper bound of A. So U has to be less than or equal to B for every upper bound B of A. So, and please remember, all less than equal here are clearly less than equal, which could be the actual less than equal, or could be dividing, could be subset, so any poset. Similarly, we can define the greatest lower bound for a set. Similarly, let's say L in S is called the greatest lower bound for S for A if L is a lower bound for A, and L, basically I can say C is clearly less than or equal to L for every lower bound C of A. Okay, again, as you can guess from the name, greatest lower bound means, first of all, it has to be a lower bound. And among all lower bounds, it has to be the least one, meaning that if there is a lower bound, let's say C, among all the lower bounds, it has to be the greatest one. So if there is a lower bound C for A, the greatest lower bound has to be, of course, bigger than equal to the arbitrary lower bound. So again, bigger than equal, here is a clearly bigger than equal. So C is clearly less than equal to L, or L is clearly bigger than equal to C if C is in relation with L. Now this clearly less than equal to can be the actual less than equal, or dividing, or a subset. So let's look at an example. Let's say S equals 1 to 10 with the actual less than equal. Find okay, let's say, or let me say S equals Z and A equals this. Find the least upper bound and greatest lower bound of A. So here 10 will be the least upper bound for A. So the claim is 10 is the least upper bound. Why is that? Because first of all, 10 is, how can I show something is the least upper bound? First of all, it has to be an upper bound, because 10, because as we say, A is less than equal to 10 for every A in A. This is the meaning of upper bound. Upper bound has to be bigger than equal to every element of your set. Well, 10 is bigger than equal to every element of my set, so it's an upper bound. 10 is an upper bound. And also 10 is less than equal to B for any upper bound B of A. 10 is an upper bound, is also the least upper bound, meaning that is less than equal to any upper bound B of A. Why is that true? Since if not, we would have B less than 10. And this is contradiction with B being an upper bound of A. Right? My claim is 10 is less than equal to B for any upper bound B of A. Why am I saying this? If not, but B will be less than 10. But if B is an upper bound, it has to be bigger than equal to every element of A, and 10 is one of the elements of A. So B has to be bigger than equal to 10. It's not possible that B is less than 10. So similarly, check that the greatest lower bound is 1. Check that 1 is the greatest lower bound of A. So one notation, the greatest or the least upper bound of a set A is denoted by supremum of A, also called supremum of A. And the greatest lower bound of a set A is denoted by infimum of A, and also called infimum of A. Okay, so supremum is the least upper bound. The notation is SUP of A, and infimum is greatest lower bound, and the notation is INF of A. So in example above, thus in example above, what could we say? We could say that supremum of A is equal to 10, and infimum of A is equal to 1. So, and in the, one thing I want you to notice is that in this example, 10 is also maximum element of A, which turns out to be supremum as well. And 1 is the minimum element, which turns out to be infimum as well. So, and this is always true, and maximum is always supremum, and minimum is always infimum, if they exist. So supremum is not necessarily maximum, however, and infimum is not necessarily minimum. So one direction holds, the other direction no. So let me give you as a maybe proposition. If A is a set such that a maximum A exists, then maximum A, so this means maximum, but max I mean maximum, then maximum A is same as supremum A. Also, if minimum A exists, again, this means minimum, then minimum A is equal to infimum A. Okay, and before proving this, let me give you the remark that it is possible that for a set supremum A exists, but maximum A does not exist. For example, if you set, for example, it's A equals open interval 0 to 1, then maximum A does not exist. No element is the maximum, but supremum A is equal to 1. Can check this, you'll see the proof in Math 225 or analysis course, analysis 1. Okay, but intuitively, if I want to explain, supremum is, or in other words, the least upper bound is 1. Well, there are many upper bounds for this set. For example, 1 is one of them, 2 is one of them, 2.1 is one of them, but the least upper bound is 1. And so supremum is 1, and maximum does not exist because, well, 1 is not an element of A, right? So we cannot say maximum is 1. Maximum has to be inside A, but 1 is not inside A. So 1 is not an option, but any other number you consider in A is not a maximum. For example, if you say 0.9 is not a maximum because, for example, 0.99 is in A and is bigger than 0.9, so 0.9 cannot be maximum. Similarly, 0.99 cannot be maximum because we have 0.999, which is bigger than 0.99. So 0.99 is not maximum either, and so on. Okay, so similarly, it is possible that infimum A exists and minimum A does not exist. Again, you can consider A equals open interval 0 to 1. Then we can say infimum of A is 0. And minimum of A does not exist. The greatest lower bound is 0. But 0 is not in A, so it cannot be considered as minimum. And there is no minimum for A, again, because if you consider 0.1, for example, it's not minimum because 0.01 is less than that and is inside A. 0.01 cannot be minimum because 0.001 is inside A and less than 0.01, and so on. Again, the proofs you'll see in Math 225, but that's the idea, basically. So let's prove the proposition that we said here. If A is a set such that maximum exists, then maximum is supremum. And similar version for a minimum and infimum. So proof of proposition. So let's call maximum A as M. Then by definition of maximum, what can we say? We can say that A is less than equal to M for every A in A. Remember, when we are talking about a set A or a set S, we're talking about a post set here, right? And a post set is always equipped with a relation of the form Kerley less than equal, which can be also denoted with R. But Kerley less than equal is easier. So I have a post set here. S and A is a subset of that. Those are assumed implicitly. And maximum A, I'm assuming it exists. I want to show it's equal to supremum. So first of all, I call the maximum M. Then by definition of maximum, we can say that A is less than equal to M for every A in A. Right? And so that means M is an upper bound because every A is less than equal to M. So that means m is an upper bound for A and is also the least upper bound. So this means, so this implies that m is an upper bound for A and is also the least upper bound. Also, how can I show it's the least upper bound? I have to consider another upper bound for A. Also, if let's say B in S is an upper bound for A, then we can say that B, can say that M is less than equal to B. If I prove this, then that means M is the least upper bound because it's the less than equal to any other upper bound. If not, what can we say if M is not less than equal to B? Well, we can say that, M is not less than equal to B, and this is contradiction with B being an upper bound for A, right? B is supposed to be an upper bound for A. Upper bound for A means that it has to be bigger than or equal to every element of A. And M is one of the elements of A. Remember, M is supposed to be maximum, and maximum by definition always lies inside the set. So B has to be bigger than or equal to every element of the set, and one of the elements of A is M. So B has to be bigger than or equal to M as well. So this means that M is the least upper bound of A, because we show that it's an upper bound and it's the least among all other upper bounds. So M is the least upper bound of A, and therefore that means M, which was a notation for maximum of A, is equal to supremum of A. Similarly, show that minimum of A is equal to infimum of A. Okay, example, let's say S equals 2, 4, 20. Find 3 upper bounds. Or let's say S equals Z again. A equals this. Find 3 upper bounds for A and find supremum of A. So S equals Z, by the way, the relation here is just the usual less than equal. So S equals Z with standard less than equal, and A is equal to this 3 upper bounds for A and supremum of A. So 3 upper bounds for A. What do you want to list? 3 upper bounds for A. We could say, let's say U1 equals 20, U2 equals, let's say 21, U3 equals 22. Because we have for every A in A, we can say that A is less than or equal to U1. Similarly, for every A in A, we can say that A is less than or equal to U2. And for every For every A in A, we can say that A is less than or equal to U3. So U1, U2, U3, these are upper bounds for A because they are bigger than or equal to every element of A. Remember, the upper bounds do not have to be inside the set A. They have to be inside the universal set S. My S here is Z, so my upper bounds are required to be in S, but not necessarily in A. But one of them, 20, is in A as well, which happens to be maximum as well. And we already said that and proved that whenever we have maximum, that maximum will be upper bound, the least upper bound automatically. 3 upper bounds, and since maximum A exists and is 20, and by proposition above, we can conclude that a maximum A equals supremum A equals 20. We just said that, if maximum exists, then it will be automatically same as supremum of your set. Okay, so let's look at another example. Let's say this time S equals Z or N with dividing relation. And let's say let A equals 2, 4, 5, and 8. Find, again, 3 upper bounds for A and supremum of A. Does maximum A exist? So 3 upper bounds for A. So upper bound means an element which is bigger than or equal to every element inside this set. So let me start with the hash diagram again. These type of questions is easy to handle with hash diagram. So hash diagram, we have 2 here, and then we have 4 on top of 2, and then we have 8 on top of 4, and then we have 5 here. So 5 is like same level of 2, and there is no element on top of 5, and 5 is not on top of any other element either. So for upper bound, we need some element which is on top of all of them, right? So remember, in this type of diagram, if B is on top of A, means B is bigger than or equal to A, right? So now upper bound means an element which is bigger than or equal to every element in the set. So, and bigger than or equal, like I said, means above, being above that element in the diagram. So I need to find an element which is above all these elements, all these 4 elements. What can I consider? Well, 8 is already above 4 and 2. So let's say if I multiply 8 with 5, which I get 40, then 40 will be on top of 8 and also on top of 5. Right? Because when I multiply 8 with 5, I get 40, and 5 becomes a factor of 40. 8 also becomes a factor of 40. That means 8 divides 40, and 5 divides 40. So 40 will be on top of 8. Once it's top of 8, it will be top of 4 and 2 as well, because 8 itself is on top of 4 and 2. And also 40 is on top of 5. So 40 is top of everything, meaning that it's bigger than equal to, but by bigger than equal here, we mean curly bigger equal. So bigger equal, curly bigger equal here is the dividing relation. So I found an element which is on top of all the remaining elements or all elements of A. So here we have 2 divides 40, 4 divides 40, 8 divides 40, 5 divides 40, and that means 40 is an upper bound for A. Another upper bound, let's say if I consider, for example, 40 times 2 or 80, again, same thing happens, 2 divides 80, so 80. 80, how do I get 80? I just multiplied 40 by 2 because 40 is already multiple of all the elements of A. So if I consider a multiple of 40, that element will be again automatically multiple of these 4 elements. So 2 divides 80, 4 divides 80, 8 divides 80, 5 divides 80. So 80 is also an upper bound for A. Similarly, for example, I can multiply 40 by 3, I have 120, which is 40 times 3, is also an upper bound for A. So we found 3 upper bounds for A. And supremum. So supremum, my claim is 40 is the supremum, least upper bound, the least upper bound. So we already showed that 40 has an upper bound, but why is it the least upper bound? To claim supremum of A is equal to 40, because first of all, 40 is an upper bound. For A, which was proved above. Also 40 is less than equal to curly less than equal. Remember here, the relation is not actual or standard less than equal, it's dividing, but still we can denote it with curly less than equal. B, for any upper bound B of A. Why is that true? Since 8 divides B, right? And 5 divides B. B is an upper bound, meaning that every element of A is curly less than equal B. Curly less than equal here means dividing. So 8, which is one of the elements of A, divides B. 5, also element of A, divides B. But from number theory, we know that if 2 relatively prime number divides B, then product of them will also divide B. So that means 40 divides B, because if A divides B and let's say C divides B and GCD of A and C is 1, then AC will divide B. So 40 divides B, so we show that 40 divides B, which means 40 is curly less than equal to B. Well, that's it. So we show that 40 is the least upper bound. So it's an upper bound, and among all other upper bounds is the least one. So 40 is the least upper bound of A, and that means supremum of A is equal to 40. And it also asked, does this set have a maximum? 2, 4, 8, 5. It does not have a maximum, because maximum must be an element which lies above everything. But there is no element here which lies above everything in the original set. So remember, in the original set, we don't have 40. We didn't have 40. It's just 2, 4, 5, 8. If we had 40, then yes, 40 would be a maximum, because 40 is above everything. But 40 is in S, not in A. If it's in S, not in A, it would not be considered as maximum. It would be only considered as upper bound. So 40 is an upper bound, but not a maximum, because it's not inside A. So A does not contain any maximum, since no element of A in Hash diagram lies above all other elements. Here's the Hash diagram again, 2, 4, 8, and 5 here. But if we didn't have 5, also 8 would be maximum, is above it, would be above everything. But 8 is not above 5, because 5 does not divide 8. Okay, so this is about maximum. So let me add part B of this question. Is, let's say, 42 an upper bound for A? So A is this set. And remember, A was 2, 4, 5, 8. Can we say 42 is an upper bound for A? In other words, can we say every element of A is less than or equal to 42? Well, here it's a little bit tricky. Remember, when we say less than equal, we mean clearly less than equal. It means the relation that we are, is defined on the set. We have to consider that relation. It could be a standard less than equal, or it could be other types of relations, such as dividing. Here in this example, we are saying that S is n with dividing relation, not the standard less than equal. So of course, yes, if it was standard less than equal, every element of A would be less than equal to 42, obviously, and 42 would be an upper bound. But with this relation, dividing relation, well, 2 is, dividing relation means the clearly less than equal is dividing. So does 2 divides 42? Yes. So 42 is above 2. Does 4 divides 42? No. And also 5 does not divide 42 either. 8 does not divide 42 either. So 42 is only on top of 2, not on top of the remaining 3 elements with this relation, with dividing relation, and therefore is not an upper bound, because for upper bound, it has to be above everything in the set. So let me say it this way. So the answer is no. For example, 4 does not divide 42. So that means 4 is not clearly less than or equal to 42. And therefore 42 is not an upper bound for A. Okay, so be careful, it's a little bit tricky. But if the relation was the standard less than equal, yes, then 42 would be an upper bound for A, because bigger than equal to every element of A in the standard concept of being bigger than equal. But in this case, bigger than equal or clearly bigger than equal comes from dividing, and 4 does not divide 42, so 4 is not clearly less than equal to 42. And part C, as an exercise, you can repeat this example and find 3, this time lower bounds, and infimum of A, and find infimum of A. And you can also answer the question that does minimum of A exist? Another exercise, let S with clearly less than equal be a poset, and A is a subset of S. Suppose that supremum of A exists, show that supremum of A is unique. Is unique. Whenever you want to prove the uniqueness in mathematics, you know what to do. You can consider two elements, let's say B1 and B2, both of them being supremum of A, and then show that B1 must be equal to B2. This is one common way to show that an object is unique in mathematics. We can assume there are two of them, let's say B1 and B2, both being supremum of A. And if we show that B1 is equal to B2, then that means supremum must be unique. And because supremum is unique, that's the reason that we call supremum the least upper bound, because there's only one of them. If supremum exists, there's only one of them. Similarly, we can do the same argument. Similarly, if infimum of A exists, then it will be unique. Okay, and again, for this reason, infimum of A is called the greatest lower bound, because there's only one of them. Okay, guys, so this is the last section and that we want to cover in this course. So thank you, and yeah, next week we will have the final exam. I'll send you email about some details about the final exam. Okay, so thank you and see you.